Hello everyone, thanks for joining. I'm Bridget and I'm part of Group 7. We will be discussing solar panels and wettability. I will first touch on some important background information, then hand it off to Letitia, Jared, and Mihir in that order. Photovoltaic cells are made by doping boron and phosphorus on silicon, which allows for the creation of p-type and n-type semiconductors in the cell. The p-type could be thought of as positively charged and the n-type as negatively charged. When light reaches the cell's depletion layer, electrons move from the n-type to the p-type layer via an external path, and this flow of electron provides a direct current. When dust accumulates on the solar panel surface, less light reaches the depletion layer and the overall cell efficiency decreases. These efficiency losses can be caused by reflectivity or accumulation of dust, sand, or snow. With particle accumulation, we can see significant losses of 10 to 20% with dust, while snow can reduce efficiency by 1 to 5%. These numbers may not seem significant for a single household, but will accumulate over time, especially for larger implementations. Traditional methods for cleaning solar panels, such as water or manual labor, are time-consuming and costly. Rather than waste resources, we can use low-power methods like electrostatic or use hydrophobic surface coatings. Superhydrophilic and superhydrophobic coatings facilitate the removal of deposited dust, which increases the light transmittance and efficiency. In superhydrophilic surfaces, water droplets wet the surface and form a film of water that washes away all contaminants. In superhydrophobic coatings, due to high water contact angles, water droplets easily roll off the surface, thereby removing contaminants on their way off.
The design of a superhydrophobic surface should be able to sustain the impact pressure of a raindrop without transitioning from the Cassie-Baxter into the Wenzel state. Now, raindrops are formed in the troposphere, but they reach terminal velocity before reaching the surface. This happens because the weight of the drop becomes equal to the drag force slowing it down. For an average raindrop size with radius of 0.2 centimeters, C is estimated to be 0.5, which gives us a terminal velocity of 9.3 meters per second. Now we can calculate the impact pressure caused by a raindrop on a superhydrophobic surface by applying the terminal velocity into the Bernoulli equation, which gives us a delta P of 43.5 kilopascal. Here we decided to add a 10% safety margin and got a final impact pressure of 47,850 pascal. We know that a raindrop can wet the surface by impalement or sliding. Here, let's assume that our surface is made of circular pillars, and let's calculate what would the height and diameter of those pillars be in order for our surface to sustain the impact pressure. First, let's assume sparse pillars. By assuming P, which is the distance between consecutive pillars, equal to 5h, and making the impalement pressure equal to the impact pressure, we find height to be 60 nanometers. Therefore, in a sparse pillars configuration, H has to be greater than 60 nanometers to prevent wetting by impalement. Now, to increase the breakthrough pressure, let's try out dense pillars. In this case, after following the exact same procedure as in the last slide, we notice there is a relation between H and R that must be obeyed in order to prevent wetting. And if we assume H to be 60 nanometers, then R has to be greater than 2.4. So let's work with a surface where P is equal H, which is 60 nanometers, and R is 10 nanometers. We know this surface should be able to resist wetting by impalement, so let's analyze if it's also able to prevent wetting by sliding. The first step before calculating the sliding pressure is to estimate the total solid area in contact with the raindrop, or phi s. Here phi s is the area of the circle over the area of the square, and for our surface it's equal to 0.049. Since this is a superhydrophobic surface, the water contact angle has to be greater than 150 degrees, and the advancing angle should be greater than that. So let's assume theta A is 160 degrees. Now we have everything we need to calculate the sliding pressure, which is 2.9 megapascal. This pressure is 2 orders of magnitude greater than the impact pressure, which means this surface should be able to resist wetting by both impalement and sliding.
We will now talk about the impact of roughness on wettability. Depending on whether the surface has a hydrophobic surface coating or a hydrophilic surface coating, roughness on the solar panel is impacted differently. We will use Wenzel roughness as it is known from the Wenzel equation that roughness magnifies wettability of the surface. We will consider two cases, one where we use a hydrophobic coating and the other where we use a hydrophilic coating. We will consider both cases in regards to the Wenzel equation individually to determine what would be the ideal surface coating type in regards to roughness. Assuming the values of the distance between the two pillars is 60 nanometers, the height of the pillar is 60 nanometers, and the radius of the pillar is 10 nanometers, we find the length of the triple contact line to be 200 nanometers and the projected length to be 80 nanometers. This gives us a resulting Wenzel roughness value of 2.5. This is applicable for both the cases as the structure for both cases, hydrophobic surface coating and hydrophilic surface coating, are assumed to have the same structural dimensions. To find out if the condition of the Wenzel equation is met, we must first find out the apparent contact angle of both the cases. In, in terms of case 1, hydrophobic surfaces have a contact angle of above 90 degrees. We assumed that our contact angle was 111 degrees so that we could receive an apparent contact angle of 153.6 degrees. This satisfies the condition that as long as the Wenzel roughness is greater than 1 and the contact angle is greater than 90, its respective resulting apparent contact angle shall be greater than the contact angle. In the second case, for hydrophilic surfaces, the contact angles are generally less than 90 degrees. So we assumed that that a theta contact angle value would be 69 degrees. On further calculations, our apparent contact angle was calculated at roughly 26.4, which also satisfies the condition that if, as long as roughness is greater than 1 and our contact angle value is less than 90 degrees, its resulting apparent contact angle shall be less than its respective contact angle. Jared will later go over how roughness also affects transmittance and reflectivity.
Superhydrophobic surface coatings are used on solar panels to encourage moisture to bead up and roll off due to low contact angle hysteresis, but they aren't perfect. Compared to superhydrophilic coatings, they have a lower moisture accumulation rate, meaning dew condenses on the surface at a much lower rate. This may sound like an ideal situation, and in most cases it is. However, when concerned with having a self-cleaning surface, it is actually preferred to have a higher condensation rate, which comes from superhydrophilic surface coatings. One of the ways to get an efficient self-cleaning surface is to make a hybrid surface. It must allow moisture to easily condense on it, utilizing hydrophilic surfaces, but let that condensed water run off readily, utilizing superhydrophobic surfaces. One way to achieve this is by starting with a hydrophilic surface, such as glass, and applying a superhydrophobic surface coating to it. Then expose small portions of the underlying hydrophilic surface by drilling or etching. This makes for a surface that has a self-cleaning trait. Dew readily condenses on the hydrophilic sections, and when the droplet becomes large enough to touch the hydrophobic surface, it slides off, taking the dust with it. Roughness on a surface affects how the light behaves when it strikes. A higher roughness causes scattering of light and is best suited using what's known as a diffuse model for predicting reflection. A low roughness or a flat surface is best suited for a specular model and is not diffuse at all. This is assuming a perfectly flat surface. A more reflective surface means less light will have a chance to pass through, which leads to transmissivity. Transmittance is the ratio of light falling on a surface to the amount of light passing through. A high transmittance would indicate that most of the light landing on the surface is passing through. Transmittance is also dependent on roughness, where a higher roughness will likely have a lower reflectivity and therefore a better chance of transmittance. The reason there's only a better chance is because transmittance also depends on the material properties of the object in question. Because solar panels rely on sunlight to create power, reflectiveness and transmittance play a huge role in the efficiency. A small increase in efficiency can mean megawatts of power in the long run. For this reason, we want a low reflectiveness and a high transmittance. which in both cases a high roughness is needed. Superhydrophobic surfaces are most frequently used, while hybrid surfaces are being used for specialty applications. The lotus leaf is an excellent example of this. The superhydrophobic surface repels water and toxins, keeping the leaf clean. Ideally, a solar panel would mimic this. To wrap up, superhydrophobic and superhydrophilic coatings help increase solar panel efficiencies by keeping them clean. This compared to untreated glass. When using hydrophobic coatings, one of the more important things to consider is the breakthrough pressure, so the surface stays in a Cassie-Baxter state and continues to repel water. Roughness from a superhydrophobic surface enhances the wettability, but also impacts reflectivity and transmittance, which means there must be a trade-off between these qualities in order to reach the best efficiency. And finally, hybrid coatings can combine positive traits from various coatings to get the most from your surface. Some questions we thought you should know how to answer from our presentation are: 1. How roughness affects wettability. 2. How roughness affects reflectivity and transmittance. And 3. Why it's important to estimate the breakthrough pressure when designing a superhydrophobic surface.